Our next unit is on energy. When we talk about energy, we first have to ask what it is. And a lot of you probably have an intuition that if you have energy, you have the ability to do something, right? And we haven't talked about it yet, and we will down the road, but energy is the ability to do work. And work has a very special physics definition. But even in your day-to-day definition of work, if you do work on something, you're applying some force and you're pushing it a distance, right? So we're going to say energy is the ability to do work. And we're going to quantify that a little bit more later on. Energy is the ability to do work. So there's many kinds of energy, lots of kinds of energy, but we're going to talk about 4 specifically that are going to be useful for a lot of the problems that we want to solve. So the first kind is gravitational potential. Gravitational potential energy. And just like when we were doing forces, and we saw that the force of gravity near Earth was mg, approximation, but the force of gravity in general between two things is gm1 and 2 over r squared, you're going to get a similar thing for gravitational potential energy. So this is gravitational potential energy near Earth. We write potential energy with a U, and it's equal to mgh, where m is mass, g is the acceleration due to gravity, 9.8 meters per second squared, and h is your height above some reference height. So usually the floor, the ground will be 0, and then this marker would be some height that you'd measure above the floor. And the type of energy this is, what it actually is I'll actually write it right next to it. So this is energy due to position. And again, the formula is U equals mgh. We also have kinetic energy. Kinetic energy. And kinetic energy is the energy of motion. If something is moving, it has kinetic energy. So kinetic energy should probably depend upon speed, right? And it does. Kinetic energy is K, and is equal to 1/2 mv squared, where m is mass and v is speed. I know it's a little weird because you're used to seeing v as velocity. Here it's speed. Energy is a scalar, not a vector. You have an amount of it. You don't have a certain direction and an amount of it. So v is speed. And that's the energy of motion. We have elastic potential energy. And this is energy due to physical deformation. So if you stretch something or compress something, you're storing potential energy in that something. One thing I want to point out too is potential energy is kind of a misnomer. It makes it sound like it has the potential to have energy, but it doesn't actually have any. That's not true. Potential energy is a type of energy. It's a stored kind of energy. It's probably called potential because it doesn't really do anything, right? You compress a spring, you sit there, it has energy, hooray. You really only see the effects of energy when energy is changing form. So from potential to kinetic, right? You see something happen there. So elastic potential energy we write as U with a subscript of elastic, and this is equal to 1/2 kx squared, where k is the spring constant. The spring constant is how stretchy the spring is. How easy is it to compress it or to stretch it apart? X is how far do you stretch it or how far do you compress it beyond the equilibrium point, which is just, if I look at a spring, it's sitting there, it's not stretched at all, that is its equilibrium point. And then I push it and I measure how far did I push it relative to what it was. Okay? So that's going to be my X. And the last thing we're going to do is gravitational potential energy, which is not near Earth. So gravitational potential, and I'll write in general. And this one is going to look very similar to our general gravity force, where I'm going to write UG is equal to negative G m1 m2 divided by r. Notice that the r here is not squared. Also note that there's a negative sign in front of it, which is a little weird. The reason for this is because Usually for this potential energy, we choose our reference point to be 0 at the ground. Here, we choose our reference point to be at that energy is 0 at an infinite distance away. All that means is as you move really far away, there's essentially no real gravitational potential energy associated with that. Good. So these are the 4 types of energy that we're going to be using a lot to solve some problems with. So now I'm going to do some examples just to familiarize you with these equations. The first thing I want to do is I want to look at the units. What are the units of energy? So we can do dimensional analysis and we can figure that out. Let's take probably the easiest equation of these, which is that U is equal to mgh, right? So let's find out what are the units of U. This is just a product of 3 things. So mass has units, we're going to take the units of mass times the units of acceleration due to gravity times the units of the height. So the units of U are equal to, well, the units of mass are kilograms. You may also see this as the units of U are units of, of mass, m. Either way that you do this is fine. The units of G, acceleration, is meters per second squared for SI units, which is length over time squared. And then height is just meters, which is length. So this gives units of kilograms meters squared over second squared, or mass times length squared over time squared. Now a newton from force, when we did force had units of kilogram meter over second squared, which was mass times length over time squared. These are off by only a factor of length, by a meter, right? So we can rewrite this as a unit of force. We could say, oh, well, this is a newton times a meter, and this is a unit of force times a unit of length. So this gives us more of an intuition for what energy is. One of these units of energy, which this, again, is messy to write out. You don't want to write out the whole thing, so we make up a name for it. This is equal to a joule, which is spelled J-O-U-L-E. And we write it just as J. Okay? So a joule is the amount of energy it takes to apply a force of 1 newton over a distance of 1 meter. That's what a joule is. And that also tells us that energy has to do with force and pushing stuff, the ability to push stuff over a distance. That we're going to get into work, which is going to be in an upcoming video. So from here, let's look at how we can use these equations to find energy. So this is just to familiarize yourselves with the equations. The actual problems that we do have to do with energy conservation. That's where you do the interesting stuff. Here, we're just going to see what happens. So suppose I have a ball. I have a ball of mass. Mass is 5 kilograms. Let's say the height is 2 meters. And I want to find potential energy of the ball. So the potential energy of the ball, U, is given by mgh. So you just plug stuff in. You have a mass of 5 kilograms. G is 9.8 meters per second squared. And then height is 2 meters. So 5 times 2 is 10, times 9.8 is 98. So U is equal to 98 meters squared kilograms over second squared, which is just equal to 98 joules. So that's what's meant by potential energy and how you go about doing that. Kinetic energy, as we said, was the energy of motion. So suppose this time I throw a ball, which has a mass of 2 kilograms, and I throw it with a speed of 5 meters per second. Well, my kinetic energy is, we write K. K is equal to 1/2 mv squared. So K is equal to 1/2 times the mass, which is 2 kilograms, times square of the speed, so 5 meters per second squared. 2 over 2 is 1, so we're left with 5 squared, so kinetic energy is equal to 25 joules. Okay, so that's how you would use values for kinetic energy. And then the last one I'll do out is if you have a spring. Suppose I have a spring like this, and I put a ball at the end of it. And then let's say I squish it. It's attached here. So I squish it, so now it's tighter, and I have this. So this was moved a certain distance. This is the x I was referring to. So let's say you push this 2 meters. Let's say this ball is 5 kilograms, not that you'll even need that. And let's say that the spring constant, which is how stretchy the spring is 5 kilograms over a second squared. Those are the units of the spring constant. It's a little weird. So I want to find the elastic potential energy, how much energy was stored in the spring. That's equal to 1/2 kx squared. So this gives me 1/2 times k, which is 5 kilograms per second squared, times x squared, so 2 meters. I square the whole thing. 2 squared is 4, 4 over 2 is 2, 2 times 5 is 10. So I get 10 joules. And that would be how much energy is stored in a spring. And this is generally how you want to, what these values mean. I'm only doing these problems to give you an idea of, these exercises, to give you an idea of what these values mean, what physical quantities they correspond to. But to do actual interesting problems with energy, you need the idea of conservation of energy, which is going to be the next video.